Hey guys, wait. Do you guys ready for our exam?
Not yet. By the way, I don't understand about topic argument.
Argument. I think I know about that topic.
Yeah.
I think we can do group discussion.
Yeah.
Let's go. Okay, let me teach you guys about argument.
Assalamualaikum. My name is Sharon Najwa binti Hazarir and my student card is 2024280096 and I will explain one of the subtopic in mathematical logical which is argument. So what is the meaning of the argument? Argument is a list of given statement called premises followed by the final statement called conclusion of the argument. The premises from hypothesis and the conclusion can be expressed as the diagram. So, one way to prove the validity of the argument is by showing the implication is tautology. Argument can also be proven by using rule of inference. As we all know, in this semester, we have learned 8 rules of inference, which is modus ponens, law of syllogism, modus tollens, rule of conjunction, rule of disjunctive syllogism, rule of conjunctive syllogism, rule of disjunctive amplification, or we know as rule of addition, and lastly, rule of contradiction. So, let's see some argument that use rule of inference.
Example 1. Solve the following argument by using rule of inference. P implies Q, Q implies S, R implies negation S, negation P or R is the premises, and the conclusion is negation P. 1 until 4 is the premises, and number 5, 1 and 2, we use law of syllogism, and we got P implies S. 6, we use 3, contrapositive, and we got S implies negation R. 7, we use 5 and 6, law of syllogism, and we got P implies negation R. 8, we use 4, definition of amplification, and we got P implies R. 9, we use 7, contrapositive, and we got R implies negation P. 8 and 9, law of syllogism, we got P implies negation P. And 11, we use 10, definition of amplification, negation P implies negation P. And lastly, we use 11, idempotent, and we got negation P. So, the argument is valid. So, example 2. If Pak Samad has enough saving, then he goes for Umrah. He is healthy or he has enough saving. He is not healthy, therefore, he goes to Umrah. First, we need to introduce by using P, Q, and R. P, Pak Samad has enough saving. Q, he goes to Umrah. R, he is healthy. So, for the solution, 1, P implies Q, 2, R or P, 3, negation R. Those are the premises. For 4, 2 and 3, we use syllogism disjunctive. So we got P. 5, we use 1 and 4 by using modus ponens, and we got Q. Therefore, Pak Samad goes for Umrah. So the argument is valid.
I know about contrapositive, converse, and inverse. Let me teach you guys.
Now, I will explain 3 logical forms of an implication, which is converse, contrapositive, and inverse. I will start with the original implication, P implies Q, which means if P then Q. First, the converse is formed by switching P and Q, so it becomes Q implies P. Next, the contrapositive is formed by negating both P and Q are reversing their position, which give not Q implies not P. This form always has the same truth value as the original implication. Lastly, the inverse is formed by negating both P and Q without changing their order, which is not P implies not Q. In conclusion, these 3 forms help us understand and analyze logical statement more clearly. Now, let's see example 1. The original statement is if the student completes all assignment on time, then the student pass the course. So the converse is, if the student pass the course, then the student completes all assignment on time. Here we simply switch this position of the statement. The contrapositive is, if the student does not pass the course, then the student does not complete all assignment on time. In this case, both statements are negated and reversed. This statement has the same value as the original implication. Lastly, the inverse is, if the student does not complete all assignment on time, then the student does not pass the course. Here, both statements are negated but the order remains the same. For this second example, the original statement is, if the student studies consistently, then the student performs well in the final exam. The converse is, if the student performs well in the final exam, then the student studies consistently. Here, the two statements are switched. The contrapositive is, if the student does not perform well in the exam, then the student does not study consistently. Both statements are negated and reversed. This statement has the same truth value as the original implication. The inverse is, if the student does not study consistently, then the student does not perform well in the final exam. Both statements are negated, but the order remains the same. So, these two examples further show how we form the converse, contrapositive, and inverse from an implication. Now, I will explain about a truth table. What is a truth table? A truth table is used to display the relationship between the truth value of proposition. Example, we use a truth table to prove the converse, contrapositive, and inverse. The original implication is, if I have the key, then I can open the door. This means having the key implies that I can open the door. The converse is, if I can open the door, then I have the key. The contrapositive is, if I cannot open the door, then I don't have the key. The inverse is, if I don't have the key, then I cannot open the door. By using the truth table, we can compare the truth value and see that the original implication and the contrapositive are logically equivalent, while the converse and inverse are not always equivalent. Now, I will show the truth table for P and Q, including their negation, not P and not Q. Here, we can see the column for P implies Q, Q implies P, not Q implies not P, and not P implies not Q. By comparing the value, we notice that P implies Q and not Q implies not P have exactly the same truth value in every row. This proves that the contrapositive is logically equivalent to the original implication. However, Q implies P, which is the converse, and not P implies not Q, which is the inverse, do not always have the same truth value as the original implication. Therefore, the truth table helps us verify the relationship between implication, converse, contrapositive, and inverse.
Hey, what are you guys doing here?
Oh, actually, we were discussing about MAT 222.
Oh, I see. I don't really understand about quantifier. Can you guys explain to me?
Yes, sure.
I can teach you.
Hi, today I'm going to explain about the quantifier, which are used to express statements involving all or some element in the sets. So what is quantifier? Quantifier are words that refer to all quantities such as some or all. We have two types quantifier, universal quantifier. The phrase for all is called the universal quantifier. It denoted by universal quantifier. The second quantifier is existential. The phrase there exist is called the existential quantifier. Is denoted by existential quantifier. Next, 3 steps to translating word statement into logical expression. First, identify the quantifier. Second, decide the domain. Third, write the predicate something happened. Now, example 1, open statement. Universal all student. PS, X visit the library.
QX borrow books, RX return a books on time. Translating the following into logical expression. A. All student who visit the library borrows a book. Keywords. All student, we use a universal quantifier. PX applies QX. B. Some students do not visit the library. Keyword some. We use the extension quantifier. Do not visit the library. Negation RX. C. All students who borrows book return them on time. Keyword all student. We use universal quantifier. QX applies RX. D. There exists a student who visits the library but does not return book on time. There exists extension quantifier. PX conjunction QX. Now we are going to look at negation with nested quantifier, which allows us to express the opposite of statement that involves more than one quantifier. Nested quantifier follow the same negation rules, just repeated for each layer. Key notes negation change the quantifier. First, change the quantifier for all to extension quantifier or extension quantifier for all. Second, bring the negation inside until it reaches the predicate. Third, use a De Morgan's law. Fourth, negation of implication. Fifth, do not change the order of the quantifier. Now, this exercise about negation with nested quantifier. A. For all x extension y, px disjunction qy. We do a negation. For all x, we change for extension x. Extension y, we change for all y. Px, we put a negation px, disjunction, negation qy. B. Extension x for all y, pxy applies qxy. So we do a negation. Extension x, we change for all x. Extension for all y, we change for extension y. Pxy applies. We do a disjunction, not disjunction, conjunction, negation qxy. C. For all y, extension x, rx, disjunction xy, we do a negation. For all y, we change for extension y. For extension x, we change for all x. Rx, we put a negation rx. Conjunction, negation xy.
Oh, now I understand.
Oh wait, but I don't understand anything about chapter 3. Can anyone explain to me?
Oh, I know about chapter 3 about forward and backward method.
And I think I know about contradiction. We can explain to you guys about it.
My name is Nurdani Sharifah binti Muhammad Jasni. My metric number 20244333124. I'm going to explain what is actually forward and backward method. This is the first method that we must approach when we want to prove any problems regarding to the proving method. All of the proof method rely on this method. This slide explains the forward and backward method, which is used to prove mathematical statement of the form if A then B. In this type of statement, A is hypothesis or assumption and B is the conclusion. First, the backward method start from the conclusion B. We ask what condition must be true for B to hold and we work backward step by step until we reach A. This method is mainly used to plan the proof and understand what we need to show. Next, the forward method begins by assuming A is true. We then use the given information in A and apply logical rules step by step to derive new statement until we finally reach B. This method is used to clearly write out the proof in a logical order. Together, the backward method helps us plan the proof while the forward method helps us complete the proof logically. So, there are 3 steps in forward and backward method. Step 1. identify the statement. Step 2, use backward process. And step 3, use forward process until the backward and forward is equivalent. This is example 1. Step 1, identify the statement. N is any integer will be statement A, which is our hypothesis, while n squared plus n is even will be statement B, which is our conclusion. And then, the step 2 will be the backward process. Statement B1, n squared plus n equals to 2k for some integer k. Next, step 3. Use forward process until the backward and forward equivalent. Since the statement C that n equals to even integer, so n equals to 2m for some integer m, and then statement A2, we need to substitute n equals to 2m into this expression and we get 4m squared plus 2m. Then, we factor out 2 and obtain 2m squared plus m. Next, statement A3, we simplify statement A2 and we get n squared plus n equals to 2k where k equals to 2m squared plus m. Now we can see that the statement A4 is equivalent to B1. Okay, so this is example 2. We are given that triangle ABC is a right angle isosceles triangle. This is our assumption labeled as A. Our conclusion labeled as B is that the perimeter of triangle ABC is square root 2 plus 2 times one of the congruent sides. First, using the backward method, we start from the conclusion. We express the perimeter as square root 2 plus 2ab and use this step to plan what we need to prove. Next, we apply the forward method by assuming A is true. Since the triangle is isosceles, AB is equal to BC. The perimeter of triangle ABC is the sum of all its sides, which is AB plus BC plus AC. Using the Pythagorean theorem, we find that AC equals to square root AB square plus BC square. By substitute AB for BC, we simplify the expression and obtain the perimeter as square root 2 plus 2AB, which match the conclusion. Therefore, the statement is proven.
I'm going to explain about the contradiction method. So the contradiction method is when we assuming the opposite negation of what you want to prove, using logical reasoning to derive consequences from this assumption, showing that these consequences lead to a contradiction, something impossible, false, or inconsistent, concluding that the assumption must be false, so the original statement is true. These are the steps in contradiction method. Step 1. State the proposition. Step 2. Assume the negation. Step 3. Work through the assumption. Step 4. Identify the contradiction. And lastly, step 5. Conclude. Example 1. Okay, so we assume to the contrary that R is a rational number of the form R equal to P over Q, where P and Q are integers with Q not equal to 0, and that R squared equal to 3. Furthermore, it can be assumed that P and Q have no common divisor. It follows that 3 equal to P squared over Q squared, or equivalently 3Q squared equal to P squared. Since 3 divides P squared, it follows that 3 divided P. Thus, there is an integer k such that P equal to 3k. Substitute P, 1 obtain Q squared equal to 3k squared. From this, 3 divides Q squared, so 3 divides Q. Thus, P and Q have the common divisor, which cannot be. Hence, R is rational. R is irrational. We are given quadratic equation ax squared plus bx plus c equal to 0, where a, b, and c are all odd integers. The goal is to prove that this equation cannot have a rational solution. To apply the contradiction method, we begin by assuming the opposite. Suppose there is a rational solution, say P over Q, where P and Q are co-prime integers, and at least one of them is odd. Substituting P over Q into the equation gives us multiply P over Q square plus B multiply T over Q plus C equal to 0. And then we multiplying through by Q square to eliminate the denominators, and we get AP square plus BPQ plus CQ square equal to 0. Now, observe the parity of each term. Since A, B and C are odd and P, Q are integers, each term is odd if P and Q are odd. The sum of three odd numbers is also odd, so the left-hand side would be odd. But the right-hand side is 0, which is even. This creates a contradiction. An odd number cannot equal an even number. Therefore, our assumption must be false. The quadratic equation cannot have a rational solution if all coefficient is odd integer. Circle with center O and a tangent line N that touch the circle at point A. The goal is to prove that the tangent line is perpendicular to the radius OA. To apply the contradiction method, we begin by assuming the opposite of what we want to prove. Suppose the tangent line M is not perpendicular to the radius OA. Then, there must exist another point B on line M such that OB is perpendicular to M. Since A is the point of tangency, point B must lie outside the circle. This implies that OB is longer than OA. However, triangle OBA is a right triangle with OA as one of its sides. In any right triangle, the hypotenuse is the longest side, so OA must be longer than OB. This leads to a contradiction. We cannot have both OB to OA and OA equal to OB. Therefore, our initial assumption must be false. The conclusion is the tangent line to a circle is always perpendicular to the radius that connects the center to the point of tangency.
To conclude our presentation, we have covered Chapter 2 and Chapter 3. In Chapter 2, we learned how to determine whether an argument is valid. We also studied the main method to prove argument, which is the rules of inference. In Chapter 3, we learned how to write valid argument using mathematical language. Some of the methods discussed include the forward-backward method and the method of contradiction. Overall, this chapter helped us improve our logical thinking and problem-solving skill in mathematics.
Oh, now we understand.
So we are ready for exam.
Let's go!
Let's go. Yay.